Hey guys, so we are going to talk about Charles's law today. So it's the effect of temperature changes on volume. Okay, so as the gas inside of a balloon cools, the average kinetic energy of molecules decreases. Okay, we talked about kinetic energy before. Okay, so with fewer and less collisions, the gas molecules move closer together and occupy a smaller volume than they previously did. Okay, because again, they're colder, there's going to be less movement of those molecules, so they don't move as far, they're closer together. Okay, so the volume decreases, assuming that no change in the amount of gas and pressure. Okay, so with that explanation, we would actually end up with an equation that looks like this: V1 over T1 equals V2 over T2. So at a constant pressure, the volume of a gas is directly proportional to the temperature in Kelvin. Okay, so if you guys actually tried this experiment at home, you blew up a balloon and then you measured the circumference of your balloon. Okay, if you stuck it in the freezer, you guys should find that your balloon, after I would say a few minutes, you guys should actually see that your balloon should have gotten smaller. Okay, because remember, with the decrease in temperature, your gas particles are moving slower. They occupy less space, so your volume is going to decrease. Okay, and then if you take that same balloon and you took it outside on a hot summer day, you left it outside for a few minutes, okay, you'll see, take that circumference of the balloon again, you'll see that the balloon increased in size. And again, that has to deal with the kinetic energy, the kinetic molecular theory. Okay, the more movement we have, okay, the more collisions we have, the more that they're going to be bouncing around, increasing your volume of that balloon. Okay, so observe what happens to the balloon as liquid nitrogen is being poured on it. Okay, so you'll see liquid nitrogen is extremely cold. Okay, you actually need gloves to handle liquid nitrogen, or else you'll get freezer burns, chemical burns. Okay, so you'll see that as they pour that liquid nitrogen on it, it starts cooling those gas particles immediately. And then those gas particles just deflate. Okay, so helpful hint, if you think of your equation, if you put your equation in a box, it kind of looks like an elevator. So Mr. Charles is the elevator operator. Thelma, temperature, and Violet, volume, are best friends. And of course, you know how best friends are. Wherever they go, the other one goes too. So if they both go up the elevator, Thelma and Violet will also go up. So that's just kind of a helpful hint. Okay, and then gas expanding and contracting. Remember, at low temperatures, okay, we have less movement, so the mercury should stay at a lower volume, and then at higher temperatures, your gas is going to start expanding, colliding more. Okay, and then that little mercury is going to go higher up your capillary tubing. Okay, so guided practice. And some reminders: temperature must be in Kelvin. So if you're ever given degrees Celsius, don't forget to convert to Kelvin. Okay, so number one, the temperature of a 0.65 liter sample of carbon dioxide gas is 580 Kelvin. If the pressure remains constant, what is the new volume of the gas if the temperature increases to 1300 Kelvin? Okay, so let's identify our variables. We have 0.65 liters, so that's going to be our initial volume, and it's at a temperature of 580 Kelvin, so that's going to be our initial temperature. Our question is asking for the new volume, so that's going to be our final temperature, and then our final volume. And then our final temperature is 1300 Kelvin. So if we plug in all our variables into our equation, it should look something like this. And again, when you deal with fractions, you're going to want to cross multiply. So we're going to cross multiply 0.65 times 1300 Kelvin, and then we're going to multiply 580 Kelvin by our unknown V2. Okay, so again, to solve this, we're going to multiply these two values, and then we're going to divide by 580 so we can find out what our unknown is. And the value that you get should be 1.457, which rounds to 1.5 with the correct number of significant figures. Okay, now if you want to do number 2 on your own, please go ahead and pause the video, but if not, number 2, a balloon has a volume has a balloon of 5.6 liters at a temperature of 98 degrees Celsius. If the volume of the balloon increases to 9.5 liters, what will be the temperature of the gas in Celsius? So assume that the pressure remains constant. Okay, so if we identify our variables, we are given 5.6 liters, so that's going to be our initial volume. Okay, and we're also given 98 degrees Celsius. Okay, but again, we don't use 98 degrees Celsius, so we're going to have to convert that to Kelvin. And then we also have 9.5 liters. That's going to be our V2, and it's asking for our temperature in Celsius. Okay, so if we plug in our variables into that formula, okay, it's going to look something like this. And of course, to solve for an unknown that is in fraction form, we're going to cross multiply. And we will get 5.6 times 371 Kelvin. Okay, and then don't forget we did change our 98 degrees Celsius to 2 Kelvin by adding 273. Okay, and then we're going to set that equal to 9.5 liters times our unknown T2. When you multiply those values and then divide by 9.5, you should get 218.7, which rounds to 220 degrees Kelvin. But you know what? I think I actually forgot to convert it back to degrees Celsius like the question had asked. So if we take 220 and subtract that to 273, then our final answer is actually going to be negative 53 degrees Celsius. Okay, so please make that correction. Your final answer should be negative 53 degrees Celsius as your final temperature. Okay, if you guys have any questions, please let me know, comment, or ask me in class. You'll have a good one.